Okay, class. Good evening. I hope my slides are visible to you and I'm audible to you. So, I welcome you all to today's class. This is the sixth tutorial for the course Symmetry, Stereochemistry and Applications, which is conducted by NPTEL. Whose course instructor is Professor Anshuman Roy Chaudhary from Mysore, Mohali. I am Deepika, your PMRF teaching assistant. I am doing my PhD in chemistry at IIT Bombay. So, till now, we have conducted 5 tutorials for the course where we have been learning various concepts on symmetry and stereochemistry. So, in this week, the video lectures which were available were focused on diastereoselectivity of cyclic molecules. So, we are not going to cover the theoretical part, we will just solve a few more conceptual questions on the topics which have been covered lately. Okay, so let us go through the questions. Identify all asymmetric centers in the molecules below and classify the molecule as chiral or achiral. So here we are given a library of molecules. You have to do two things. First, you have to identify all the asymmetric centers present in the molecule, and also you have to classify the molecules as chiral or achiral. So you must know that it is not necessary that if a molecule has a chiral center, it will be chiral as a whole, okay? Because when it comes to meso compounds, in those compounds we have chiral centers present, but the compounds as a whole are not chiral, okay? So whenever there are meso compounds present, we have to be careful, okay? So let us go one by one and let us identify the asymmetric centers first, and then we will decide it is a chiral molecule or achiral molecule. So in the first molecule present, this is an asymmetric center because this particular carbon is linked to 4 different groups, okay? One of which is hydrogen, one is this methyl, and 2 are alkyl chains, which are the 2 chains from the cyclohexane molecule, okay? So this will be the first chiral center present in the molecule. And secondly, this center will also be an asymmetric center because this is also linked to 4 different groups, where one is this methyl, the other is a hydrogen which will be above the plane, which is not shown here, and 2 of these will be the alkyl chains which complete the cyclohexane moiety. So thus this first molecule has 2 different asymmetric centers. Now we are going to figure out this molecule is a chiral or achiral. So this molecule does not have a plane of symmetry. You can even figure out the absolute configuration of these 2 carbon atoms. So we have to announce that this first molecule is chiral, okay? Now let us come to the second molecule. In the second molecule, this center which is present here is asymmetric because it is linked to a methyl group, an ethyl group, the chloro substituent, and also there will be one hydrogen present here which will be below the plane. Okay, hence four different groups are linked to this particular carbon atom. That is why this will be the asymmetric center present. And when it comes to chirality, it will be chiral because it does not possess a plane of symmetry. So this molecule will also be chiral. Now we will go to the next molecule. So in the next molecule, if you ask about the presence of asymmetric center, at a first glance, you may think that this carbon atom, which is present here, can be asymmetric. But no, if you look closely, these two linkers are the same. Okay. As well as these two methyl groups are also the same. So, this center does not possess different substituents. Okay, all four substituents at this carbon are not different. That is why there are no asymmetric center present in the molecule. And this molecule will also possess a plane of symmetry. Hence, this is found to be achiral. Okay. Then we will go to next molecule. Here, if we see the asymmetric centers, this particular center will be one asymmetric center because it is, oh sorry. So in the fourth molecule, if we look at these two centers, they may look like asymmetric centers, but again in this one, these two are methyl groups. Okay, in both the centers, two of the substituents are methyl groups. Hence, this molecule again does not possess a center which is linked to four different groups. This is why there is an absence of asymmetric center in this molecule as well. Moreover, this molecule is symmetric. Hence, this molecule will also be achiral. Okay, I hope this is clear to you. Next, we will move to the next molecule. Here we have two centers, okay? So in this molecule, these are the two centers which are not linked to similar groups, okay? Both the two centers are containing four different substituents. Hence, these two will be the asymmetric centers present in the molecule. Also, if you look closely, this molecule does not possess any plane of symmetry. So, this molecule will be chiral. Now, let us move to the next molecule. which is 1,2-dichlorocyclohexane. So here we have two asymmetric carbon centers. Okay, because both these centers are linked to one chloro substituent. One will be hydrogen, one alkyl chain, and the next one is also an alkyl chain, which is chloro substituted at the alpha position. So these two are going to be the asymmetric carbon centers present. But this molecule is going to be a meso compound, okay? Because you can split this molecule into two equal halves via an axis which is going to pass through this. Okay, this will be a plane of symmetry which is going to split this molecule into two equal halves. Hence, this compound will be a meso compound and it will be achiral. Next, we have this molecule where we have two asymmetric centers. Why not three? Because this center is not asymmetric because it is linked to two identical substituents. Okay, these alkyl chains will be exactly identical. Hence, these two substituents will be the same. This is why this third center is not going to be asymmetric, but these two centers are going to be asymmetric. Now, if we place a mirror here, this will resemble a plane of symmetry which is going to divide the molecule into two equal halves. Okay, so this is why this molecule will also not be chiral and it will be a meso compound. Next, again, we have another meso compound where a plane of symmetry can pass through it and it can divide itself into two equal halves. But it also possesses two asymmetric carbons. Hence, although this molecule is having two asymmetric carbons, the molecule as a whole is achiral and is a meso compound. In the next molecule also, a mirror plane passing through it can divide this molecule into two equal halves. Hence, the molecule will be achiral, but it will possess two asymmetric centers, which are these two. Ah, these two will not be asymmetric centers because each of these carbons are linked to these two substituents and these two are identical at this center. Hence, 2 out of the 4 substituents are identical and the centers will not be, that is why asymmetric. For this center also, these two substituents will be the identical and this center will also not be asymmetric. Hence, this molecule is not having any asymmetric carbon and it is achiral. So let us move to the next molecule. In this molecule, this carbon will be the first asymmetric carbon because it is linked to 4 different groups, as well as this carbon is linked to 4 different groups, hence it is also asymmetric. But if you look at this carbon will not be asymmetric because it is linked to 2 identical substituents. But since this molecule does not have a plane of symmetry, hence this molecule is going to be a chiral molecule. Again, the next molecule is also not having a plane of symmetry, hence this molecule will also be a chiral molecule and these two will be the asymmetric centers present in this molecule because this and this methyl and another hydrogen, these are the 4 different groups present at the carbon center. So in this one, again if you look at, this can be divided into 2 equal halves through a mirror plane passing through it. Hence this molecule will be achiral. Also there will be no presence of asymmetric center because these two substituents are identical, which are linked to both the methyl and hydroxyl groups. Lastly, in this molecule, this carbon is asymmetric carbon as well as this carbon is also asymmetric carbon and also it does not have a plane of symmetry, hence this molecule is going to be chiral. So I hope it is easier for you now to identify the asymmetric carbons and chiral versus achiral molecules. Next, let us move to a few more questions from the same topic. Which of the following terms best describes the pair of compounds shown, enantiomers, diastereomers, or the same compound? So you are given a wedge dash representation of a molecule and a Fisher representation of the same molecule. Okay, so to check whether these compounds are enantiomers, diastereomers, or the same compound, let us assign the absolute configuration to the chiral centers present in the molecule. Okay, so in the first molecule, if you look at this carbon center, is the asymmetric carbon. So let us try to assign the absolute configuration to this particular carbon. So this will get the priority 1, this will get priority 2, this will get the third, and this will get 4. So fourth group is present in the plane, as you see. So to assign the absolute configuration, we have to exchange two of the bonds. Okay, so at first, if we exchange 4 and 1, the representation will change into 4, 1, 2, and 3. So if we go from 1 to 2 to 3, it will be S, as the fourth priority group is above the plane. So the absolute configuration will be S. Then for the next molecule, you see this is the asymmetric carbon present. Okay, so this is going to get the first priority, this is going to get the second priority, this is going to be the third priority, and this is going to be the fourth priority. Hence, if the fourth group in the Fisher projection is present in the horizontal plane, we have to exchange or reverse the absolute configuration which we get from moving from 1 to 2 to 3. Hence, as this representation is giving us R, the absolute configuration will be S. Hence, both the compounds which are given are having S absolute configurations. Hence, out of all the three terms which are given, you will have to choose the option that the pair of compounds given are the same compounds. Okay. Similarly, we are going to solve this question. Okay. Which of the following terms best describes the pair of compounds shown? Enantiomers, diastereomers, or the same compound? So again, we are going to assign the absolute configuration to the asymmetric carbons present. First, for this center, this will get the first priority, this will get the second, and this will get the third. So the first center is having R configuration, and for this one, this will be 1, this will be 2, and this will be 3. So the second one is also having R configuration. Then here, this will be 1, this will be 2, and this will be 3. it will be R 1, 2, 3, S. You can take your time and solve it slowly. Okay, so as you can see, the first compound is having a pair of stereocenters RR, and the second pair is having a pair RS. So if RR is having an opposite of RS, these two will be a pair of diastereomers. Okay, and if you are asked to identify the enantiomers of these two pairs, RR would have an enantiomer with a pair SS, and the RS will be having its enantiomer with a pair SR. Okay, so when it comes to the given pair of compounds, these two will be a pair of diastereomers. So in the first question, label each asymmetric carbon in the compound below as R or S. So there is only one asymmetric carbon present in the first compound, which is this one. Okay, so you have been asked to identify the absolute configuration of this center. So this OH group will get the first priority. The handle with the olefin on it will get the second priority. The other alkyl chain of the cyclohexene ring will get the third priority and methyl group will get the fourth priority. Hence, if you move from 1 to 2 to 3, the absolute configuration of the chiral center is S. There will be no reversal of the absolute configuration because the fourth priority group is present below the plane. Okay, so let us do the same with the next question. Label each asymmetric carbon in the compound below as R or S. So there are two asymmetric centers present. One will be this carbon which is towards us and one will be the other carbon which is away from us. So let us try to draw the Fisher projection so that it becomes easier for us to solve this problem. Okay. For that, we are going to rotate the molecule by an angle of 60 degrees so that it becomes eclipse. Okay. So we have converted the Newman projection given to its Fisher projection first, and then we have assigned the absolute configuration to both the asymmetric carbons present in the molecule. So note down that when we are assigning the absolute configuration to the asymmetric centers in the Fisher projection, the fourth priority groups, which are the hydrogens, they are present on the horizontal lines. So that is why whatever absolute configurations we are getting, we are supposed to reverse them. Okay. So the compound is having RR configuration. I hope this is clear to you. Again, for the third molecule, we have two asymmetric centers here. So we are going to assign the RS configurations to both the centers. So for the first one, this will be the first priority. This will be the second priority. This will be the third priority. And this is going to be the fourth priority. So on moving from 1 to 2 to 3, the center is S. For the second asymmetric center, we have this as the first priority, this as the second priority, and this as the third priority, and the fourth priority group will be away from us, which will be a hydrogen. Hence, this is also having the absolute configuration S. So thus we have assigned the RS absolute configurations to all the asymmetric carbons present in these three molecules. In the next question, you have to just identify how many asymmetric carbons are present in the compound below. So we have already done that in our previous questions. In the first one, there will be, this will be the one, this is the second one, this will be the this will be the third one, and this will be the fourth one, and this will be the fifth one. Hence, there will be 5 asymmetric carbons present in this molecule. The next molecule, this will be one asymmetric carbon, and this will be the other. Although there will be a plane of symmetry in this molecule, and this will be a meso compound, but these two will be the asymmetric carbons present in this molecule. So the number will be 2. We will just resume the tutorial. after a 2-minute break. Okay. Okay, so again, in these molecules, we have been asked to assign RS configuration to each chiral center in the compounds below. So these molecules will be the one with more number of functional groups present in them. So let us try to solve a few of them. Also note down that some of these molecules are going to have more than one asymmetric center. So you will have to assign RS configuration to each of such asymmetric carbons. Okay. So for the first one, it is very straightforward. This will be 1, this will be 2, and this will be 3. And the fourth priority group, which is going to be a hydrogen, is away from us below the plane. So this center is S. In this one, this is 1, 2, and this is 3, and the center will be R. For the third one, again, this is going to be first, this is going to be second, this is going to be third, and this is going to be the fourth one. Hence, the absolute configuration is R. For the next one, this is the asymmetric carbon. So, this will be the first, this will be the second, this will be the third, and the fourth priority group, which is a hydrogen, is above the plane. Okay, so you will have to reverse the absolute configuration from R to S. In the next one, this, 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 and this. These are the asymmetric carbons present, which are 4 asymmetric carbons present. So let us solve one by one. This will be 1, this will be 2, and this will be 3. But the fourth priority group is above the plane, and we will have to reverse it, and the center will be R. For the second one, this is first, this is again second, this is third, and the fourth priority group is below the plane. Hence, the center is R again. Now we will move to this center. So this will be 1, this will be 2, this will be 3, and the fourth will be above the plane. So we will have to reverse it, and this center will be S. And lastly, we are left with only one center. So for the last center, this will be 1, this will be 2, this will be 3, and the fourth group is above the plane. Hence, it will be S again. So all the 4 asymmetric carbons we have assigned, these two are R, and this is S, and this is also S. Okay. Then we are left with the last molecule, where this will be the asymmetric center present. So this arc will be first, then this will be second because this is alkyne, this will be third, and fourth will be below the plane. Hence, this center present is S. Let us now move to the next question. An organic compound PCH816 produces a meso compound upon oxidation with osmium tetroxide and NMO. The compound P is E4 octane, Z4 octane, E3 octane, Z3 octane. So you have to identify what will be the structure of the compound P, which is having a molecular weight of C8H16, which produces a meso compound upon oxidation. So you must know one thing, that to produce a meso compound upon dihydroxylation, the compound must be Z. Okay, the configuration must be Z of the double bond. So let us look at the concept and explanation for this question. So the reaction of an alkene with osmium tetroxide followed by hydrolysis or using osmium tetroxide catalytically with a co-oxidant like N-methyl morpholine N oxide NMO converts the alkene into a vicinal diol. Okay. The addition of the two hydroxyl group occurs exclusively on the same face of the double bond. That is, suppose this is the alkene you are having. Upon which osmium tetroxide is going to act. Okay, so the addition of both the hydroxyl groups onto the alkene is going to occur from the same face. The syn addition occurs via a concerted cycloaddition forming a cyclic osmate ester intermediate, which is then hydrolyzed to the diol. You can visualize this as such a transition state and a cyclic osmate intermediate. A meso compound is an achiral compound that possesses two or more chiral centers. It has an internal plane of symmetry. So whenever symmetric cis alkene is subjected to syn addition, we get a meso compound because of the syn diol formation. And when it comes to the trans alkene, we will get a racemic mixture or a pair of enantiomers. So here you can see the reaction of Z4 octane with osmium tetroxide and NMO where the final product will be mesodiol. And since the molecular formula of the alkane is already given, you can, at the first place, you can rule out the options which are having 3-octene as the options. Okay, so it will be either E-octene or E4-octene or Z4-octene. So since the product is given as mesodiol, you have to choose the option where it is given Z4-octene, because E4-octene is going to give us a racemic mixture. In the next question, it is asked, fumaric acid is converted to S. Okay. Fumaric acid is converted to S2-hydroxybutadioic acid by the enzyme fumarase, such as in this reaction. Okay. So fumaric acid has been converted into 2-hydroxybutadioic acid, and this stereochemistry is given to be S. So which of the following statement is true about above enzymatic conversion? The hydroxyl group is added stereospecifically from psi phase of the double bond. The hydroxyl group is added stereospecifically from re phase at the double bond. The psi and re phase gives the same product. The enzyme fumarase is not able to distinguish between these two phases. Therefore, the product should be racemic mixture. So you have to remember, since the product given is already S configuration, so you can conclude that the hydroxyl group has been added from the psi phase of the double bond. Okay, if the product is having an absolute configuration R, you can say that the addition is taking place from the re phase. I hope this was clear to you. Hence, option A will be the correct answer. So, in the next question, it is asked, which of the following pair can be distinguishable by 1H NMR spectroscopy? So, four pairs of the compounds are given. Let us check the relationships between the pair of compounds. Okay, so if we figure out for the first one, this compound is having an absolute configuration R. Okay, and this one is having an absolute configuration S. Similarly, for this one, if we check, it will be an S, and this one will be R. Okay, so first pair is R and S. The second pair is S and R. The third pair is already given as L, D and L. So these are also enantiomeric pairs. For the last one, if you see, these two are not mirror images. Hence, these are diastereomers. And you must know that enantiomers cannot be distinguished using 1H NMR spectroscopy. So, as the first three pairs are enantiomeric pairs, these three pairs will not be distinguished by 1H NMR, but the last one will be distinguished using 1H NMR spectroscopy. Again, the compound given below are regioisomers, identical enantiomers, or diastereomers. So, if we look at the presence of the deuterium substituents, one of these is present at this carbon atom and the other is present at this carbon atom. Whereas in the other compound, this deuterated substituent is present at this carbon atom and the other is present here. So clearly you can see that position of the deuterated substituents are not the same in both the compounds given. Okay, even the rotation of the compounds will not give us a similar structure with having the same bond connections. Okay, so these two compounds are not identical, neither enantiomer or diastereomer. These are regioisomers. Okay, so in the next question, among the following, the optically inactive compound is, at first we are given an amine and one phosphine and one alene and then this hydroxycarboxylic acid. So out of these four, we let us first rule out one by one. Okay, for example, for the fourth one, it is clearly having an asymmetric carbon and it is not possessing any plane of symmetry. So this compound is optically active. For this alene as well, as we have studied the substituent rules for alenes, this alene is optically active as it is not having any plane of symmetry. This phosphine as well, although having a lone pair of electron, it is having three different substituents and it is going to be optically active. But for this amine, you must know that pyramidal molecules like this amine undergo a phenomenon which is called umbrella inversion, where the molecule flips inside out through a planar transition state and it can invert itself. Okay, and because of this umbrella inversion, the amines, although having three different substituents, are not optically active because it can convert itself into different configurations via the phenomena which is called umbrella inversion. Okay, so because of this phenomenon, I'll note down here. Because of this phenomenon, these molecules are not going to show any optical activity. Okay, I hope this is clear to you. So let us move to the last question. Mark all the chirality centers in the formula of the lipid-lowering drug lovastatin, shown below with an asterisk. How many chirality centers are present here? So you can try to solve it on your own first. So the given compound lovastatin has 8 chirality centers in total, and here are the chiral centers which has been listed down. Okay, so these are the chiral centers which are present and are linked to 4 different substituents. Okay, I hope you all could figure out the total number of chirality centers present in the molecule. So with this, we have solved the questions which were in this week's tutorial, which is week 6. And thank you everyone for joining. So we will meet again at the same time for the week 7 tutorial, where we will expand our knowledge on the topics which will be covered in the week 7 video lectures, and we will be solving a few related questions with the topics which will be going to covered. Okay, so thank you very much.